Welcome back to a new session of MOOC on Information Security, Stack and Buffer Overflow. Have you ever seen a message like Stack Overflow or Buffer Overflow when working with your system? Do you know what's a buffer? It is a space of physical storage memory used to store temporary data while moving from one place to another. These buffers usually reside in RAM. Computers often use buffers to improve performance. Most modern hard drives use the benefits of buffering to access data efficiently, and many online application services also use buffers. For example, buffers are often used during online video streaming to prevent interfaces. When a video is streamed, the video player simultaneously downloads and stores 20% of the video in a buffer and then streams from that buffer. Therefore, a small reduction in connection speed or rapid service interruption does not affect the performance of the video stream. However, buffers can contain a certain amount of data that limits their ability to hold limited data for a limited time, as multiple applications use this mechanism of the buffer. Consequently, a situation arises when further data is pushed into a buffer. Such a condition refers to a term called a buffer overflow. It is a flow that arises when software that writes data to a buffer surpasses the buffer capacity, resulting in the overwriting of neighboring memory locations. That is, too much information is transmitted to a repository that does not have enough space, and this information is gradually replaced by neighboring repository data. Buffer overflows can affect all types of software. These are usually informal inputs or failures to assign sufficient space for the buffer. If the transaction violates the norms of executable codes, the program may perform variably and result in incorrect output, memory access location errors or crashes. For example, a buffer for login data can be configured to require an 8-byte username and password to be entered. So, if a transaction contains 10 bytes, that is 2 bytes more than expected of input, the program can write down excess data over the buffer limit. Buffer overflow attacks. Attackers exploit buffer overflow issues by overwriting the memory of an application. This changes the execution path of the program, triggering a response that damages files or exposes private information. For example, an attacker may introduce extra code, sending new instructions to the application to gain access to IT systems. If attackers know the memory layout of a program, they can intentionally feed input that the buffer cannot store and overwrite areas that hold executable code, replacing it with their own code. For example, an attacker can overwrite a pointer, an object that points to another area in memory, and point it to an exploit payload to gain control over the program. A buffer overflow can occur inadvertently or when a malicious actor causes it. A threat actor can send carefully crafted input referred to as arbitrary code to a program. The program attempts to store the input in a buffer that isn't large enough for the input. If the excess data is then returned to the adjacent memory, it overwrites any data already there. The original data in the buffer includes the exploited function's return pointer, the address to which the process should go next. However, the attacker can set new values to point to an address of their choosing. The attacker usually sets the new value to a location where the exploit payload is positioned. This change alters the process execution path and transfers control to the attacker's malicious code. A buffer overflow vulnerability will typically occur when code it is reliant on external data to control its behavior. It is dependent on data properties that are enforced beyond its immediate scope, or its behavior is so complex that programmers are not able to predict it accurately. Buffer overflows can affect all types of software. They typically result from malformed inputs or failures to allocate enough space for the buffer. If the transaction procedure overrides executable codes, it will cause the program to behave unpredictably and generate incorrect results, memory access, or crashes. C and C++ are two languages that are highly susceptible to buffer overflow attacks, as they don't have built-in safeguards against overwriting or accessing data in their memory. Mac OS X, Windows and Linux all use code written in C and C++. Built-in safety mechanisms used in languages like Perl, Java, JavaScript and C# minimize the likelihood of buffer overflow. Nevertheless, buffer overflows can happen in any programming environment where direct memory manipulation is allowed, whether through flaws in the programmer, runtime libraries or features of the language itself. Buffer overflow attack consequences. Common consequences of a buffer overflow attack include the following. First one is system crashes. A buffer overflow attack will typically lead to the system crashing. It may also result in a lack of availability and programs being put into an infinite loop. Second one is access control loss. A buffer overflow attack will often involve the use of arbitrary code, which is often outside the scope of program security policies. Another one is further security issues. When a buffer overflow attack results in arbitrary code execution, the attacker may use it to exploit other vulnerabilities and subvert other security services. Buffer overflow attack types. Many different buffer overflow attacks use different strategies and target different pieces of code. These are the best non-buffer overflow attacks. Stack overflow attack. This is the most common type of buffer overflow attack and involves buffer overflow in all stack. Heap overflow attack. This type of attack targets data in the open memory pool known as heap. An integer overflow attack. It occurs when an arithmetic operation results in an integer that is too large to be stored in the integer type. This may result in a buffer overflow. Unicode overflow. Unicode overflow creates a buffer overflow by inserting Unicode characters into an expected input of ASCII characters. ASCII and Unicode encoding standards that allow computers to display text. For example, the ASCII number 97 stands for the small letter A. Although ASCII codes only cover Western language characters, Unicode is the word in which characters can be created in almost any written language. If more other characters are available in Unicode, many Unicode characters are larger than most ASCII characters. Now we will move on to stack overflow attacks. The stack is a LIFO, that is last in first out data structure. It supports two operations, push and pop. The push operation is used to specify the value of the steel and the pop operation is used to extract the value of the steel. If the data placed on the stack is corrupted, it will override the adjacent memory location and affect the data or pointer already stored by the other program. Steel overflow is an old vulnerability that uses stacked memory that only exists during runtime. The vulnerability is usually in C or C++ because we are free to use the pointer in those languages. An attacker or hacker could take advantage of this vulnerability to exploit the system by manipulating data or creating a pointer to run malicious code. Heap overflow attack. A heap overflow occurs when a piece of memory is assigned to the heap and the data is returned to that memory without the data being checked. This may result in some critical data structures in the heap, such as heap headers or any heap based data such as dynamic object pointers being overwritten by the virtual function table. Integer overflow attack. An integer overflow is a type of arithmetic overflow error where the result of an integer operation does not lie in the allocated memory space. Instead of a program error, it usually results in an unexpected result. In most programming languages, integer values usually have a certain number of bits in memory. For example, the space reserved for a 16-bit integer data type may be an unsigned integer between 0 and 65,535 or a signed integer between 32,768 and 32,767. However, what happens if you calculate 32,767 plus 1 and try to store the result that exceeds the maximum value for the whole type? Because most languages and most compilers make no mistakes at all and only perform a modulo, accept or truncate operation, it only crashes and puts you at risk of attack. Most integer overflow conditions simply lead to erroneous program behavior but do not cause any vulnerabilities. However, in some cases, integer overflow may have severe consequences, like manipulating financial calculations or causing a customer to receive a debit instead of credit or something alike. Unicode overflow attack. Unicode strings have been introduced to ensure flawless transcription between all languages of any country. For example, Arabic characters are different from English characters. This realized that such characters could not be converted according to the available ASCII codes. Any character can be used with Unicode strings, and the Unicode schema allows the user to take advantage of the program by typing Unicode characters in input that expects ASCII characters. When the program is expecting ASCII input, it simply provides input that surpasses the maximum limit to make a buffer overflow with uncertain characters of Unicode. Prevention of buffer overflow attacks. Application developers can prevent buffer overflows by building security measures into their development code, using programming languages that include built-in protection and regularly testing code to detect and fix errors. One of the most common methods for preventing buffer overflows is avoiding standard library functions that have not been bounds checked, which includes gets, scanf and strcpy. Another common method is to prevent buffer overruns by using bounds checking that is enforced at runtime. This automatically checks that the data returned to a buffer is within the appropriate boundaries. There are several ways to prevent buffer overflow attacks from happening, including the following 5. Use operating system runtime protections. Most operating systems use a runtime protection such as the following to make it harder for overflow buffer attacks to succeed. Address space layout randomization or ASLR. Buffer overflow attacks typically need to know where executable code is located. ASLR moves at random around the locations of data regions to randomize address spaces, which makes overflow attacks almost impossible. Data execution prevention. This method prevents an attack from being able to run code in non-executable regions by flagging areas of memory as executable or non-executable. Attackers may look to override the structured exception handling override protection or SCHOP, which is a built-in system that manages hardware and software exceptions. They do this through a stack-based overflow attack to override the exception registration record which is stored on the program's stack. The CHOP prevents attackers' malicious code from being able to attack the SEH and use its override exploitation technique. Keep your devices patched. Vendors issue software patches and updates to fix buffer overflow vulnerabilities that have been discovered. There is still a period of risk between the vulnerability being discovered and the patch being created and deployed. Follow the principle of least privilege, POLP. Users and applications should only be given the permission they need to do their jobs or perform the tasks they are assigned. Following a POP approach reduces the potential for a buffer overflow attack to occur. When possible, only grant temporary privileges to users and applications and drop them once the task has been completed. Use memory-safe programming languages. The most common reason why buffer overflow attacks work is that applications fail to manage memory allocations and validate input from the client or other processes. Applications developed in C or C++ should avoid dangerous standard library functions that are not bounce-checked, such as gets, scanf, and strcpy. Instead, they should use libraries or classes that were designed to securely perform string and other memory operations. Better still, use a programming language that reduces the chances of a buffer overflow, such as Java, Python, or C#. Validate the data. Mobile and web applications developed in-house should always validate any user input and data from untrusted sources to ensure they are within the bounds of what is expected and to prevent overlay long input values. Every application security policy should require vulnerability testing for potential input validation and buffer overflow vulnerabilities prior to deployment. Implementing security measures around development, code, and operating systems is not enough to protect organizations' systems. When a buffer overflow vulnerability is discovered, it is crucial to quickly patch the software and ensure it is made available to all users. Buffer overflow attack example. A common buffer overflow example is when an attacker injects their malicious code into corrupted memory, or they may simply take advantage of the buffer overflow and the adjacent memory corruption. For example, a simple buffer overflow can be caused when code that relies on external data receives a gets function to read data in a stack buffer. The system cannot limit the data that is read by the function, which makes code safely reliant on users entering fewer than buffer size characters. This code could look like this. Buffer size is defined while defining the character buff and gets buff. Buffer overflow and web applications. Attackers use buffer overflows to corrupt the execution stack of a web application. By sending carefully crafted input to a web application, an attacker can cause the web application to execute arbitrary code, effectively taking over the machine. Buffer overflow flows can be present in both the web server or application server products that serve the static and dynamic aspects of the site or in the web application itself. Buffer overflows found in widely used server products are likely to become widely known and can pose a significant risk to users of the products. When web applications use libraries such as a graphics library to generate images, they expose themselves to potential buffer overflow attacks. Buffer overflows can also be found in custom web application code and may even be more likely given the lack of scrutiny that web applications typically go through. Buffer overflow flows in custom web applications are less likely to be detected because There will normally be far fewer hackers trying to find and exploit such flaws in a specific application. If a flaw is discovered in a custom application, the ability to exploit the flaws other than to crash the application is significantly reduced by the fact that the source code and detailed error messages for the application are normally not available to the hacker. Notable examples of buffer overflow attacks. The fact that buffer overflow continues to rank as one of the most common security vulnerabilities in software despite being known to the security community for many years is somewhat surprising. Buffer overflow attacks have been responsible for some of the biggest data breaches in history. Some of them are the Morris worm. The Morris worm of 1988 was one of the first internet distributed computer worms and the first to gain significant mainstream media attention. It exploited a buffer overflow vulnerability in the Unix SendMail, Finger and RSH REXEC systems, infecting 10% of the internet within 2 days. The Morris worm exploited over 60,000 machines between 1988 and 1990. It has sometimes been referred to as the Great Worm or the Great Daddy when it comes to the buffer overflows because of the devastating impact it had on the internet at that time, both in overall system downtime and in psychological impact on the perception of security and reliability of the internet. SQL Slammer was a 2003 computer worm that exploited a buffer overflow bug in Microsoft's SQL Server and desktop engine database products. It is a small piece of code that does little more than generate random IP addresses and send itself out to those addresses. If a selected address happens to belong to a host that is running an unpatched copy of Microsoft SQL Server Resolution Service listening on UDP port 1434, the host immediately becomes infected and begins spraying the internet with more copies of the worm program. A patch had been available from Microsoft for 6 months prior to the worm's launch, but many installations had not been patched. SQL Slammer caused a denial of service on some internet hosts, ISPs and ATMs, as well as significantly slowing overall internet traffic. It spread rapidly, infecting 90% of vulnerable hosts, about 75,000 victims within 10 minutes according to Silicon Defense. In May 2019, Facebook disclosed a vulnerability that affected all of its WhatsApp products. The vulnerability exploited a buffer overflow weakness in WhatsApp's VoIP stack on smartphones. This allows remote code execution via a specifically crafted series of SRTP, that is Secure Real-Time Transport Protocol packets sent to a target phone number. An exploit of the vulnerability was used to infect over 1,400 smartphones with malware by just calling the target phone via WhatsApp voice, even if the call wasn't picked up. In particular, the spyware infection of the phone of a UK-based attorney involved in a high-profile lawsuit generated a lot of media attention. Facebook responded by releasing security updates that fix the buffer overflow issues. Hence, in this session, we have discussed in detail the program threats like stack and buffer overflow. Hope this session was useful for you while using internet and other social media. Hope you enjoy this session. See you next time. Bye.